Hello and welcome to all students. In this lecture, we learn about exact differential equation and the solution of exact differential equation. First of all, we define what is meant by exact differential equation, and then we see the procedure of solving exact differential equation. In section 7, it was noted that when an equation can be put in the form of a into ax dx plus by dy equal to 0. This is actually a differential equation which is in variable separable form. A set of solutions can be determined by so our differential equation, if our differential equation is in this format, ax dx plus by dy, means it is in variable separable form, then by taking direct integration we can solve that differential equation. We can write or we can find the solution of that differential equation. A set of solutions can be determined by integrating, that is by finding a function whose differential is ax dx plus by dy. That idea can be extended to some equations of the form mxy dx plus nxy dy equal to 0. So here m and n, they are functions of x and y, in which the separation of variables may not be possible, and this equation is not in variable separable form. Suppose that a function f of x comma y can be found that that has for its total derivative the expression mdx plus ndy mdx plus ndy, that is derivative of f is equal to mdx plus ndy. So we call it is equation number 2. Then certainly f of x comma y equal to c, that equation number 3 defines implicitly a set of solutions of 1 for from 3. It follows that derivative of f df is equal to 0, or in view up to mdx plus ndy equal to 0 as desired. Two things then are needed. First, to find our under to find out under what condition on m and n a function f exists such that its total derivative is exactly mdx plus ndy. And secondly, if those conditions are satisfied, actually to determine the function f, if a function f exists such that mdx plus ndy is exactly the total derivative of function f, we call equation 1 an exact differential equation. If the equation mdx plus ndy equal to 0 is exact, then by definition f exists such that derivative of f is equal to mdx plus ndy. Df is equal to mdx plus ndy. But from calculus, df is equal to dou f by dx dou f by dou x into dx plus dou f by dou y into dy, and we compare these two equations and we will see that m is equal to dou f by dou x and n is equal to dou f by dou y. These two equations leads to dou m by dou y is equal to dou 2f by dou y dou x, and dou n by dou x is equal to dou 2f by dou x dou y. Just we are differentiating with respect to y and x, these two equations. Again from calculus, we know that the second order partial derivatives, they are always equal if our function f is a continuous function, provided that these two partial derivatives are continuous. Therefore equation 1 is an exact equation, then provided that these two partial derivatives are continuous. Okay, therefore, if one is an exact equation, then dou by dou y is equal to dou m by dou y equal to dou n by dou x. Dou m by dou y is equal to dou n by dou x. Thus, for one to be an exact, it is necessary that 4 is satisfied. Let us now show that if condition 4 is satisfied and 1 is an exact equation, phi of x comma y be a function for which dou phi by dou x is equal to m. The function phi is the result of integrating m dx with respect to x while holding y constant. Now dou phi by dou y dou x is equal to dou m by dou y. Hence, if 4 is satisfied, then also dou phi by dou x dou y is equal to dou n by dou x. Let us integrate both sides of this last equation with respect to x, holding y fixed in the integration with respect to x. The arbitrary constant may be any function of y. Let us call it b dash y for ease to indicate its integral. Then integration of phi with respect to x yields dou phi by dou y is equal to n plus b dash y. Now the function f can be exhibits, namely f is equal to phi xy minus by, for which if we take a total derivative of function f, we get df is equal to dou phi by dou x dx plus dou phi by dou y dy minus b dash y dy equal to m dx plus n plus b dash y dy minus b dash y dy is equal to m dx plus n dy. Hence equation 1 is exact and we have completed a proof of the theorem. Okay, so this is the proof which gives the conditions on this is the proof which gives us a condition on condition for a differential equation to be exact. Okay, and that condition is dou m by dou y equal to dou n by dou x. So theorem, if m n dou m by dou y dou n by dou x are continuous functions of x and y, then the necessary and sufficient condition that m dx plus n dy equal to 0 to be exact is that dou m by dou y equal to dou n by dou x. So that is very important condition for the differential equation m dx plus n dy equal to 0 to be exact. Furthermore, the proof contains the germ of the method for obtaining a set of solution, a method used in example A and B below. Okay, let us see some examples on exact differential equation. Okay, so consider example number 1. Solve the equation is given here, 3x into bracket xy minus 2 dx plus x cube plus 2y dy equal to 0. First, from the fact that dou m by dou y is equal to 3x square and dou n by dou x is equal to 3x square. Okay, so here m and n. So what is m here? M is 3x into bracket xy minus 2, and what is n here? N is x cube plus 2y. So we consider the partial derivatives. Partial derivative of m with respect to y, it is 3x square, and partial derivative of n with respect to x is 3x square again. So we see that these two partial derivatives are same. Therefore, dou m by dou y is same as dou n by dou x. We conclude that equation 7 is exact. Therefore, its function f is equal to c, where dou f by dou x is equal to m 3x square y minus 6x, and dou f by dou y is equal to n, and it is x square x cube plus 2y. Equation 9. Let us attempt to determine f from equation 8. Integration of both sides of 8 with respect to x, holding y constant, yields f equal to x cube y minus 3x square plus ty. Y is a function of x. Sorry, t is a function of y. And finally we get the solution: x cube y minus 3x square plus y square is equal to c. Now let us see the another method to solve the exact differential equation. Example 2. So there are many examples which here given to solve the exact differential equation, but I will tell you a short formula to solve the exact differential equation. So consider the equation 2x cube minus xy square plus 2y plus 3 dx minus x square y plus 2x dy equal to 0. This is the differential equation, and we write here m and n, and we consider the derivatives, partial derivatives of m and n as dou m by dou y and dou n by dou x. We observe that these two partial derivatives are same, and that partial derivative is minus 2xy minus 2. Therefore the equation 11 is the exact differential equation. Okay, and we solve this exact differential equation by using the formula. See here I am telling you a formula: integration of m dx, at that time keep y constant, plus integration of terms in n which are free from x dy is equal to c. So this is the formula for solving the exact differential equation. We use this formula to to find the solution of that exact differential equation. So see here once again. So I am telling here a formula: integration of m dy, at that time we keep y constant while taking this integration, plus integration of terms in n which are free from x dy is equal to c. C is a constant, integrating constant. So okay, so let us use this formula to find the solution of exact differential equation. There are lots of homework is given to you. You can take a screenshot and try to solve these examples. Okay, and in the next lecture we will learn about the linear differential equation. Okay, so let us we stop here. Thank you very much.